we're super excited to invite on stage Mr. Ilyas Khan and Promit Moitra, who are going to be in conversation talking about quantum computing. Before we get started, I'd like to give all of our attendees a very quick introduction of our speaker. Mr. Ilyas Khan is the CEO and founder of Cambridge Quantum Computing. Prior to CQC, he was the founding chairman of the Stephen Hawking Foundation. He's a fellow of St. Edmund's College at the University of Cambridge and is regularly involved in commentating on topics related to quantum computing. He has a long-standing interest in the foundation of mathematics and category theory and is a life member of the American Mathematical Society. Thank you so much, Mr. Khan, for joining in. It's an absolute pleasure to host you at ISF. A quick introduction for our ISF interviewer. We have with us Promit Moitra. Promit has been associated with India Science Festival for the past 1 year and is currently working as a postdoctoral research associate at the Institute of Plasma Research in Gujarat. So, Promit, over to you. Please take the session ahead and let's take the fireside chat ahead with Mr. Khan.
All right. I hope I'm audible.
Yeah.
Yeah, okay. Good evening, everyone. Welcome to the fireside chat to the India Science Festival. Welcome, Ilyas.
Yeah, hi. Good afternoon. Good evening, everyone.
So, well, let's get right into it. I would like to start by asking you a little bit about your journey into quantum computing. So what I saw was that your background was in banking. I've heard a lot of people going from academia into industry, but this is a rare transition. So I would like to know a little bit more about it.
Yeah, no, actually not as mysterious as it sounds, Promit. I wish there was more mystery to it. I went back to Cambridge about 10 years ago, a little bit more, and got very involved with the business school there, where I'm still a fellow. And in fact, I'm the leader in residence at the Judge Business School at Cambridge. And I started, along with two other people, something called Accelerate Cambridge, which was a way of trying to find out how deep science could be commercialized. Now, historically, the United States has had a much better track record at doing this. The hubs around Stanford and obviously the West Coast generally, the hubs in the East Coast. And in the United Kingdom, whilst we have a thriving technology sector, we weren't doing so well on the deep science side. Now, of course, with the benefit of hindsight, Accelerate Cambridge is a major success, but I was one of the founders of it at the time. I was also, as I think Shruti mentioned, I was lucky to be the chairman of the Stephen Hawking Foundation. And Stephen, of course, needs no introduction, sadly no longer with us. And it was really a confluence of those two things, the sort of the entrepreneurship around deep science, and then this insight that Stephen gave me. And it was in November 2013 when he basically said to me, you know, this is for real. Because for 30 years, there had been this caution about engineering qubits. How do you create qubits? I know you'll get into that later. So that was really it. And I can't imagine a technology that affects humankind more than quantum. Nothing in the span of human history, nothing compares with quantum. And this industrial technology revolution that we're living through, you're much younger than me, you'll be experiencing this for the rest of your life. This profound change in the nature of reality was what interested me. And so I started the company, I should say the venture, in the middle of 2014. And then since then, I've done nothing else.
Well, thank God for that. I mean, actually, I wanted to ask you about this, a bit of a meta question, as in, do you think research, or I should rather say targeted research, progresses better as an entrepreneurship venture, or like what's different between research in a lab and research as a business? So,
well, I mean, yeah. Look, I think that this is very much one of those questions where you will not get objectivity.
Okay.
And the reason for that, it's a bit like me, talking about my children being the most beautiful children in the world, right? I mean, how can they? But I think there is an interesting strand here, and I think I know where you're coming from. Let me make 3 points. I mean, the single most obvious channeling of research was in the late 1944, 1945 period, the Manhattan Project.
Right.
And we know what happened there. But the Manhattan Project was obviously built on 15 to 20 years of academic research previously, right? Yeah. So what was the difference, Promit? The difference was resource, the equivalent of billions of dollars of resource. Now, what is happening in quantum? Second point. This is the only time that I'm aware of, literally in our history, where nation states have made a single technology their priority. The US has a congressional bill that was passed in 2020 only for quantum. The German chancellor, the one that's just retired, Angela Merkel, said there's an existential risk to the future economic survival of Germany unless we compete in quantum. The Brits were there early. Japan, in China, it is embedded in the 5-year plan. Since 2013, it's the #1 technical priority. Nothing else. Now, why Italy, Netherlands, Sweden, I mean, you name it, France. Right. Now, this partnership between government and large organizations, Alibaba, Google. I mean, you should listen to a speech by Satya Nadella, the Microsoft CEO. This unprecedented allocation of resource, it is unprecedented, is the difference why the ability of organizations to make engineering advances far outstrips the ability of any single research organization. Now, if you look away from CERN and the advanced nuclear particle research, if you look outside of that fundamental research, quantum is the one area where literally there are billions of dollars being spent in order to advance engineering so that you can commercialize this. And there are different strands of this, but on this occasion, the answer is yes, it is more channeled. Now, there's an ethical yes, right? Who should this belong to? Should it belong to humanity or should it belong to individual organizations and governments? And unfortunately, I mean, it depends on your opinion, but this is my opinion, governments have gotten it along and governments are generally not cooperating. Right. I mean, one of the great sadnesses is that despite 6 years of me speaking to India, I mean, of course, we do now have a program. India should be at the forefront of this. India could revolutionize its economic well-being, but unfortunately, Indian entrepreneurs, they want to make money tomorrow. They don't care about it. So Microsoft, Google, IBM, Intel, Amazon, you name it, these huge organizations allocating research over the last 5 or 6 years to build quantum computers.
Wow. Seems like there's a geopolitical race on to master this technology. And I mean, we'll talk about a little bit more about the program in India, maybe towards the end, but this is very interesting.
Yeah, I don't think we can call the Indian initiative a program. I think that flatters it. Let's hope somebody's listening here and we do have a program. We have the talent. We have the talent, right?
Definitely, yeah. I mean, research has been given quite a bit of priority in the, I would say, last couple of decades, and a lot of institutions have been heavily funded. So this shouldn't be that hard to imagine. In 20 years, we haven't produced enough talent to actually start working on this. Something like
this. No, in Indian technologies, technologists are at the forefront. I mean, the brain drain in medicine, the brain drain in so many areas has happened even before you were born, Promit. We've been facing this problem because of the nature of academia. But just finishing on the previous point, not specific to India, No, I do think that it is a question of resource. So there are certain challenges where you need to win a Nobel Prize to have a breakthrough. That is always going to be in a research environment, at Princeton or IAS or, many of the organizations, Cambridge, etc. But then once you're beyond that, once you're beyond fundamental breakthrough and you're looking at applications and engineering, then you need resource. And that then needs managing, that needs money, it needs focus. And that's where I think entrepreneurship and then large corporate focus comes to play. My own personal view is that the winner, so earlier this month, Apple became a $3 trillion company.
Yeah.
Right? $3 trillion. Right?
More than nation states GDP, yeah.
Yeah, that's right. So in 15 years' time, 10 or 15 years, which is not long, the likelihood is that the largest company in the world will be a quantum company. And it won't be 3 trillion, it'll be many trillions, more than that. Wow. And that is not an existing company. That will be a startup. Today, that is a startup. Right. It is not incumbents who will conquer this. It is something that's fresh. So, I said your question had two parts to it. That's the second part.
Right. I get it. This is really interesting. Just the process of the development of a technology in general. Okay, so let's get right into what quantum computing actually is. How familiar are quantum computers going to be? Is it still going to be like input, process, output, or the regular way we interact with computers, or is it something radically foundationally different?
Well, it is foundationally different, right? Okay. So for 70 or 80 years, the idea of a computer, I mean, this thing here that, I have no idea how it works, but I use it. Right. And we all use it. I drive my car. I have no idea how it works, but I drive it. So the interface with technology, as far as quantum is concerned, I think is something which probably we don't need to waste time on. It will be a reasonable interface. But I think foundationally, there are things that we now know. So first of all, the advent of quantum mechanics as a science back in 100 years ago, effectively, and the people who were involved in that discovered that the nature of reality is fundamentally different at the micro level compared to the macro level. Yeah. So the macro level is the one that you and I live in. So when I go like this thing falls, right? That's gravity, we understand it. But the rules are different. And then the rules of logic are different, Promit. First order logic is different in a quantum environment. This contrived logic that Turing came up with, I use contrived, who am I to comment on Turing? Sorry. The logic that we use in order to compute that Turing formalized and people like Shannon and Lonzo Church and others developed, this is really very limiting. We are incredibly amazed by miniaturization and speed and et cetera, but actually it's a very clunky thing. It's very contrived. The speaker earlier was saying about AI, etc. It's artificial. It's not real. Whereas a quantum computer shifts the boundaries of what can and cannot be done. That shifting of the boundary is why I said earlier, it's the biggest revolution in humankind ever. We invented fire, or we discovered fire, we discovered the wheel, we discovered heavier than human muscle lifting capability, weaving, spinning. Then we invented the steam engine, and then we discovered railroads and things. All of these things are amazing. They changed humanity. But really, did they? Did they really? No. This changes humanity.
Wow.
That's how fundamental this is. This is really profound. That's why it's geopolitical. That's why it's geostrategic.
It just immediately makes me ask. I have to ask you about the implications, because, what kind of
let me just finish the last bit of your previous question.
Sure.
The problem is you're very smart and you ask very profound questions and they cannot be answered in one sentence. So let me just finish that there. So the about 40 odd years ago, 3 or 4 people simultaneously thought about computing not using this on-off dimension, right? The transistor, right? So I don't know how many billions of transistors there are in this thing, but instead of that, using the bit becomes a physical thing. Now, what could it be? It could be a photon. I mean, it's mind-boggling. A single photon. It could be a single electron. It could be an atom, right? What happens? They said, what happens if we use physical instantiation? This is what became known as a qubit, a quantum bit, instead of a bit. That investigation, that debate led to the theory of quantum computing. Yuri Manin, David Deutsch, and Feynman. These are the names of people. They're very well documented. There's lots of material on the internet. That's how the qubit came to be born as a thing. And when you investigate that, you realize that the rules, the nature of reality is different. And as you progress, the first algorithms were invented in the mid-80s, the mid-90s, and people realize that there are certain things that you can do with a quantum computer that you simply cannot do with an existing computer. So that's the answer to your question.
So I do understand why you described logic as being contrived, because 0 and 1 are sort of abstractions of, some physical phenomena. But whereas I think in quantum computers, what you're describing is we are actually bringing in an element of reality itself into the process of computation. I mean, if I have understood it at all, but this is a really interesting aspect of.
I think you in a quantum state, Promit. I mean, this is a little bit hypey, and I'm sure there are many of your audience here who are going to throw up now. But if I may just be a little bit more popular, in the continuum between 0 and 1, there are an infinity of states. Right. So when we look at a transistor and we force it to be a 0 or a 1, are we capturing the nature of reality? And the answer is no. Right. So if you think of it in that way, it helps you understand a little bit more about what's going on. But there are various implications. When we talk about this idea of, this is obviously gets into the philosophy of mathematics as well. But, how do we manipulate things, numbers, and how do we manipulate equations and the excluded middle? All of these things become really important once you start looking at the quantum world.
Right. So the name of this session is actually kind of misleading. It's not just computation in nanoseconds. It's not just faster brute force, but it's actually, there are, like you described, some problems which are quantum native, so to speak, like only quantum computers can solve those kinds of problems.
Oh, yeah. Faster is because we understand fast. So there are certain things that will become faster, but that's not really the point. That's right. Okay.
So, yes, I'm sure this is the question in everyone's mind right now. Like, what are the implications? So one thing that we have read in popular science or press releases is that, like, once quantum computers become a reality, it's the end of encryption as we know it. And what are some implications of, or what are some of the kinds of problems that quantum computers will be able to solve, which we aren't even considering right now? I'm sure you have a glimpse into that being a vision.
I think this is, let me make one point first, which I think is very obvious. When, again, we use the example of telephones a lot. We could use the example of the internet. When new things come along, we try to imagine how they will change our world. So if you and I were talking in 1987, 1988 about the mobile phone, in its then characterization, a big brick weighing 2 kilos, etc., etc. It would have been very difficult for us to imagine how we now use them, right? Similarly, in 97, 98, I remember that was my first startup in 98, talking about the internet and how would it affect us. And it was very difficult, and we don't have the language. You know, now I say to you, Google something or let's wiki it or something, right? So with that caveat,
right,
the fact that we don't know, right? So what do we know? What can we say? I think we can say a number of things. So starting from the most important down, encryption is not important, although although many people fixate on it, and it is a huge industry and it's worth billions, hundreds of billions.
Exactly. Yeah.
But actually, in the overall scheme of things, in 200 years' time, when the history of science is written, nobody's going to say, oh my God, we had another encryption service, right? Like, who the hell cares, right? Like, who really, I mean, today we write about, yeah, you're right. So who do we remember in 100 years' time in literature? We'll remember Tagore. Is anybody going to remember the latest mystery novelist, right? So it's a bit like that. So let's look at this in terms of the impact on humanity. The impact on business and everything else then becomes more evident, and use cases become more evident. So let's just give you 4 examples. Look, there's a fundamental mystery in life. We don't understand the nature of reality. Einstein died not understanding how you can relate and make equivalent gravity and quantum mechanics. Things like non-locality, things like the mystery of the measurement, right? All these things, we don't know. If we could discover the answer to that, we change humanity. We change humanity, the Copernican revolution, the Newtonian revolution, relativity, the bomb. Right? Bigger than all of that is understanding this reality. So a quantum computer, quantum states will allow humanity to delve into the nature of reality. Don't want to get mystical and stuff like that, but it can become mystical. It can become. So that's number 1. Like, nothing's more important than that, Promit. Like, you could have $1 trillion company. It's not as important as that. So that's number 1. Then in terms of human life, we cannot today really tailor-make any medicine. We approximate these things. A quantum computer simulates a quantum system. Molecular states can then be built to order.
Wow.
This is worth thinking about. All cancers, Alzheimer's, thing of the past. Now, it has implications, longevity, like, do we want to live for 1,000 years? And these become a reality. No, young man, these become a reality. Wow. A quantum computer within the next 5 to 10 years also solves the nitrogen fixation problem. We spend an enormous amount of the Earth's output of natural gas in order to build these stupid nitrogen-based fertilizers that kill the Earth. Carbon sequestration. How many decades have we been trying to solve cancer? How many decades have we spent in the modern world trying to sequester carbon safely? These are fundamental issues. Photovoltaic. I don't know, behind you, they're real plants or they're plastic?
Yeah, no, these are real plants.
So the photovoltaic process, that plant doesn't think about anything. It does it, right?
It's designed for that, yeah.
We can replicate that.
Wow.
We can't at the moment. We're very inefficient.
So you're saying
and we haven't even started scratching the surface yet. And obviously encryption, I mean, who the hell cares? Yes, a quantum computer will crack things that are algorithmic. There may be some algorithms that are quantum secure. The world is focused on that. But that is a consequence of the fact they can do the other things, right? It's a consequence, and people fixate on it. Communication that cannot be hacked, right? That's another consequence.
Okay.
Optimization, the traveling salesman problem. At what point do existing computers explode when you try and do this, well, some people call it the nurse scheduling problem, some people call it the traveling salesman problem. I mean, these things suddenly, now, does NP hard, you understand NP hard, right? You're a computer science, yeah. So I don't know, Promit, if NP hard suddenly becomes solvable. The current consensus of informed academia is that NP hard is not solved, but the boundary shifts. So maybe things like optimization become more tractable, which means, of course, a massive impact on things like scheduling, things like logistics, optimization, Monte Carlo simulation. Now, randomness, entropy. We don't have randomness. There's no such thing as randomness. And all these people running around with these things, scattering quantum noise using photons, they're bullshit. It's just snake oil. We will be able to generate maximum entropy from a quantum computer that can be tested for independence by implementing a Mermin test or a Bell test. Imagine that.
Wow.
Right?
True randomness. Yeah.
So what does that do?
Grails, yeah.
It Holy Grail. There you go, young man. Excellent. You come and work with me. So that is very good. Now, so these are the things that I think matter.
Right. You're talking about foundational changes. Yeah, encryption doesn't even count. I mean, in that sense. I mean, and I'm sure like immediately it will be replaced by, as you said, like secure quantum communication protocols.
Yeah.
This is very interesting. So you described how we can implement qubits in photons, and you also talked about some kind of quantum phenomena going on even in plants, like the oldest kinds of life on Earth, I suppose, which has stood the test of time. And so I'm trying to understand the hardware.
Well, no. I mean, just on plants. I mean, when we try and convert light into energy, the solar power, basically.
Right.
That's what we're trying to do. We're trying to replicate the efficiency that nature is equipped with. Now, we're using it for a different reason. A plant uses it for different reasons. I'm not a biologist. So well, not even a biologist. I'm not a plantologist either. But I think that replicating that efficiency to the 90th percentile, rather than, I don't know where we are stuck at the moment, the 14th percentile, I mean, these really change things. It means suddenly we don't have to destroy the earth for mining hydrocarbons, right? And we don't have to build these bloody things that are capturing wind. I mean, it bears thinking about. We're not centuries away from this. This, I think, will happen very quickly. When I say very quickly, not next week, not next month, 3, 5 years, maybe 6, 7. That's why nation states are involved in quantum. Anyway, your next question was going to be a bit more technical. Go ahead.
Yeah, I was just this is very interesting because I have never, so we had labs which were working on macro scale quantum systems or phenomena, and what I saw, the closest thing that I've seen to a quantum computer essentially is like a tube which is hanging from a frame in the middle of a giant room, which is like, I mean, very low temperatures, very low pressures, and very hard to, like, there's a lot of input going into it just to maintain it. So when you're talking about quantum phenomena occurring in plants, which is like extremely exposed, so I'm thinking, what kind of hardware or what kind of substrates can quantum computation be implemented on?
So we don't at the moment know what will become the standard. Right? So imagine that you are a few years before the Model T Ford. So the combustion engine, maybe it's a 2-stroke engine. There aren't any gears. There's no ignition, right? We're kind of there, sort of. So what we can say is that there are a multiplicity of ways in which a qubit can be generated. Right? So when we started with classical computers, we needed switches, we needed transistors, and there were vacuum tubes and various different ways of doing this. And eventually we discovered that we could do this effectively using silicon as the medium. In quantum computing, there are a number of, remember, a quantum computer is a physical thing. It's not an abstraction. So the qubit has to be a thing. So there are people who are experimenting with something called superconducting qubits. These qubits occur, there may be electrons or atoms, at a very cold state. But this refrigeration is not, I mean, these things are no more complex than a high-performance supercomputer today. You know, if you suddenly had a supercomputer, you need a building to house it, et cetera, et cetera, et cetera. So I wouldn't get put off by the 1 Kelvin thing. Don't worry about that. That's very local. But for a superconducting quantum computer, the current favorite of most people, because these qubits can be manipulated in these temperatures, they are coherent for longer, and so therefore you can program them. When I say program, what I mean is, just as in classical computers, we have gates, we have logic gates, not and etc. Similarly, in order to implement a calculation, you have an algorithm that utilizes gates. So the measurement of these systems, the manipulation, a quantum computer has to first generate a qubit, then that qubit has to be manipulated, then it has to be measured, right? That's the essential process. So one current favorite way of doing that is using superconducting qubits. Another way is using something called trapped ion technology. And that's an equivalent way, but it's different. It's using a different approach, and there are pros and cons, which I won't go into. Then there are people who are using photonics, literally single photons, which is, by the way, which is mind-blowing, right? And then there are people who are using something called neutral atoms or cold atoms. So there are all these ways that different people are trying to use in order to build quantum computers. And just about 2 years ago, the tipping point happened when this experiment moved out of the university lab and into large-scale private sector and corporate and government areas.
Right. So, I mean, it still seems like there are a lot of challenges just to maintain this coherence that you're talking about between qubits in order to achieve quantum computation. So apart from keeping them stable and coherent, what are some of the other challenges that are yet to be overcome in order to have a large-scale production of quantum computers?
Most of the large organizations, well, even small organizations now involved. So I would encourage people who are interested in this to look at the IBM website, look at the Google website, look at my company is now the world's largest quantum computing company. It's called Continuum. Look at our website. All of the large companies and many of the small ones, Oxford Quantum Circuits, IQM, which is called International Quantum Machines, it's from Finland. There are many, many companies. They've all got roadmaps.
Right.
They've all got engineering roadmaps, very similar to what was happening in the early days of silicon-based semiconductors and other engineering. So if you imagine waking up one day in the late 60s, or actually in the late 70s when the personal computer started coming, we're now at that stage. So people have identified how they're going to solve some of the problems. The problems are stability, coherence, scaling, and then the control systems and the interface between the macro world and the micro quantum world. So there's all these different challenges where engineering is now quickly, and every week, every month now, you open up a newspaper. Well, nobody reads newspapers now. You go to your website or whatever, and there's another announcement about an advance. So just 2 weeks ago, my company announced the largest ever volume of quantum. Quantum volume is a way of measuring effectiveness. So we just hit a peak of 2048. It was less than 2 years ago that we were scrambling in the single digits.
So
we're already
that's a massive leap. Yeah.
Well, yeah, but this will become exponential.
Oh,
and we're not really going to be commercially viable in this sector in certain areas for a little while yet. But yeah, so quantum volume, and then there are other like error correcting. Just as with classical computers, you need error correcting methodologies. We need them here as well.
Right.
So there'll be advances there. There'll be advances in middleware, in compilers, in routing instructions, in the operating system. There'll be advances in application. All these things come together.
Wow. So the time frame that you're describing and the challenges that you're describing, these are compatible with each other? The challenges can be solved in the
they're
time frame
beginning to coalesce. Yeah, they're beginning to coalesce. I think the last 2 years has started to see more of this. Yeah, I think last year was a breakthrough year, 2021. Because remember, Promit, you can only effectively look forward from a solid base.
Right.
And that solid base appears to have come about last year. Yeah.
Fantastic. That's nice to know.
So, I mean, IBM are of the view, I mean, just to give you some dates, IBM have publicly said that a quantum computer that is commercially useful, where there's sustained quantum advantage, which means you can do something using a quantum computer better than you can using any other computer out there. They believe 2023, which is literally
next year.
Yeah. And then Google have gone one step further and said they believe that fully fault tolerant computers, i.e. universal quantum computers, so universality in the same way you asked me a while back about the interface, right? So universal in that context, 2029, 2030. It's nothing. Wow. So if we have a fault-tolerant quantum computer by the end of this decade, the impact on humanity is many times, many magnitudes more than mobile telephony and the internet and electricity put together.
Wow. Yeah, I thought our lives changed very quickly. We were born in the 90s and there was a constant change of devices and things that we used and the standards but what you're describing, it seems like change is going to be the norm for our lives. This is very interesting. So what you're describing is a quick question, as in, are quantum computers designed for solving specific purposes right now, or is there an attempt towards building a general purpose quantum computer?
I think there is an attempt, but at the moment it's very specific. I think that people are looking at chemistry, quantum chemistry, so simulating molecular systems like the plant behind you, although that's a while away. And then optimization, I would say, is these are the two big areas.
Okay.
And cybersecurity, I would say.
Okay. Definitely, that has to be. What's your, I came across this opinion, and since we've been talking about the plants and implementing, quantum computation going on in nature all around us. So there was this opinion by Roger Penrose, rather a hypothesis that the human brain implements quantum computation at some scale, and that is why it's been so hard to replicate, because there's this conversation between Turing and Shannon while some of their time overlapped in Bell Labs, and I read about it in some book, James Gleick's Information, right? That Turing famously said, all I'm after is a mundane brain. And he was unable to, generate that kind of behavior from his notion of logic and his design of the universal Turing machine, and which is why he designed the Turing test, I suppose. But what Penrose's hypothesis is that the human brain implements quantum computation at some scale. What's your opinion?
Well, look, Promit, this is really a big sort of question. Well, first of all, I think it's important for us to resist the temptation to get involved in a philosophical conversation, right? Sure. Because, Roger has been looking at this for all his life.
Right.
And these things started when Gödel was around, in the early 60s. And conversations about consciousness and the mind-body problem, these are, your previous speaker was referring to this. So what I would say is the following. A foundational characteristic of the human being is language.
Right.
You and I are speaking. Our audience is listening.
Right.
The magic, the mystery, the beauty of language is not currently replicable anywhere. And if anybody tells me about Siri and Alexa, they can stop right now. Alexa has no idea what you're saying. When you say to Alexa, what time is it? It burns up the equivalent of the energy that's needed for power Reykjavik for a week, and then it tells you an answer that you already know. That is not intelligence. Now, when you move from single word recognition, and remember, it's not even recognition, there's this vast network of associative words. So every time I say red, the likelihood is that Apple might come somewhere close, or Man United or whatever. That's not intelligence. That is not intelligence. So what is intelligence? If we assume that intelligence can be represented and easily understood through language, then it is very clear to me that within a few years, a computer will be capable of what is truly natural language processing in the way that you and I process language. A quantum computer.
Right.
This is revolutionary. By the way, in terms of commerce and business, this is way bigger than anything to do with cyber.
True.
Right? Can you imagine a machine that is truly
able to converse?
Yeah. So that is very a close reality. And language, the implementation of language circuits is quantum native. This was a discovery by Professor Bob Cook, also at Oxford. Now, here's the amazing thing. Today, we live in a world where large-scale AI is opaque, it is mysterious, it is dangerous. You cannot lift the lid on Alexa. So if you said to me, play me a song by Lata Mangeshkar, I don't know, Bee Gees or the Beatles or something, right?
Yeah.
If you get slightly beyond that into these systems which are whirring all around us, God knows how much information is being captured by Zoom right now, and all the 80-odd people that you've got on this thing are all busily scrabbling away. It is totally opaque. It's very dangerous. There's no accountability. A quantum computer aligned with something called compositional artificial intelligence subverts this. And I truly believe, I'm very optimistic, not just me, many people, that with a quantum computer, we can have accountable AI. Wow. Accountable AI for the first time. We are no longer hostage to these incredibly dangerous, corrupt organizations. I won't say their names. Everybody knows who they are. Yeah. We really have to make that break. And that is why I'm so excited as well, apart from medicine, apart from carbon sequestration. And I'll finish on this point. I'm the chairman, the non-executive chairman of something called the Topos Institute, TOPOS. And the Topos Institute is all about democratizing technology so that we understand what we're doing and how we do it. And quantum computers will allow us to do that. Now, I didn't answer your question about consciousness and Penrose, but actually I have, because why would we be interested in the quantum nature of the process of what we might call consciousness and the mind? We're interested because of the untapped potential that is there. There are many things that we do that computers cannot do well. So how can we align them? And that, I think, is a really interesting question. I can't answer all of it, but I do know that a quantum computer within a few years will be capable of natural language processing in a way that is accountable and transparent and no longer opaque. This is worth thinking about. Alexa, Siri, all this GPT-3, the massive cost of training neural networks, it's absolute bullshit. It really is.
So, I mean, what you're describing is so incredible, because if I had to imagine interacting with a quantum computer, if it's so capable of processing natural language, then probably we would just be conversing with them. I mean, I'm already calling it them. I don't even know.
I don't know either.
Wow.
I don't know either. But what I do know is that we're not talking about text and speech conversion. We're not talking about speech recognition. We're talking about something as close as it is possible. If we define a human being, language. I mean, there's loads of work done by Noam Chomsky and Pinker. I mean, apart from Penrose, there is some very, very good work that has withstood the scrutiny of time about the nature of language. I would encourage anybody who's interested. There's a lot of work on this, by the way, quantum natural language processing. If you Google quantum natural language processing, there have been a couple of conferences and there's lots of papers on this.
Okay, great. I mean, viewers, just pay attention. You're getting there's a gold mine right here. So get Googling right after the session. This is great. We'll come back to the point which we sort of touched upon in the beginning, the contributions from India in the quantum computational research space, and what's the scope for growth, and basically what's your advice to us?
Well, no, it's not us, it's we. We're in this together. Honestly, this is, again, you get me very agitated on this. China has the ability to catapult itself from what we used to describe as a third world status into a first world status. What does that mean? It's not about having televisions. It's not about going out to dinner every night. It's about a seat at the table of influencing the future of this planet. India should be at the forefront. This technology is owned by nobody. Nobody owns it. And it staggers me. It staggers me that titans of industry in India, that government officials, even academic institutions pay lip service. That's why I didn't like what you said earlier. There is no program in India. It's scratching the surface. The resources that we have should make India a leader. Nobody talks about India in quantum. It's along with Egypt or something. Right. It's so sad, no disrespect to Egypt. We have to be, and listen, it's not about saying, oh my God, we need this, we need this. No, we don't. We have everything. We have everything. So why do we not have a national program that is funded comparably with any other nation state? Do we really think sending a rocket up is going to help us? Do we really think that? Like, do we need another 10 satellites? Quantum is fundamental. And we know it. We don't need to guess. Like Indians, not Martians, working, like, who's the head of Microsoft? Hello. Who's the head of Google? Hello.
It should be obvious. Yeah, by now it should be obvious.
So why
lacking that vision? Long-term vision needs to be there.
No, but here in quantum, it's more specific. Why does that get lost in translation? Now, I think that it is because, and this is my honest opinion, that for the last 70 years, we have naturally assumed that technological advance means replicating, copying, and catching up to the West. It's a mindset. It's muscle memory. Right. So here, we don't need muscle memory. There is no leader. It's a fresh new technology. We don't have to go anywhere. So I don't know if there's anybody listening who cares, but if we can just have a national program, I think that would be amazing. It's not too late.
Fantastic. No, I mean, this is a very hopeful note to end on. Thank you, Ilyas. Let's take some questions from the audience. I think I see a lot of them.
I only have 5 minutes. I have to leave.
Yes. We'll just wrap this up in 5 minutes. All right. Let's see. Quantum supremacy and quantum advantage, the goal of demonstrating a programmable quantum device can solve a problem that no classical computer can. That's been answered. People are asked, okay, one solid question. Some fundamentals needed before you start learning about quantum computation. So apart from obvious quantum mechanics, what else would you suggest would be a prerequisite sort of?
Well, this is one of the reasons, going back earlier, I think India can be a powerhouse in the future. Look, I think that quantum information theory is a very new subject, and typically it's been a postgraduate subject. And I think that we're still a way away from it becoming a graduate subject. I mean, I think that it really is a combination of quantum mechanics or physics, should we say, theoretical physics and mathematics and computer science. I think that that's unlikely to change.
Okay.
And I think that there are a couple of really interesting books on this. And there's one by Professor Bob Kuka, Coecke, and Alex Kissinger, Aleks Kissinger. And it's called Picturing Quantum Processes. It's actually on Amazon. I think if there are two books that I would recommend for people who are not familiar. One is Leonard Susskind, the Introduction to Quantum Mechanics, which is nothing to do with quantum computing, but I think you need that base. It's really, really solid book. It's a thin book, but it's amazing. I normally carry it around with me in my bag, and I don't have my bag with me. That's one. And then for quantum computing, I'd have a look at Bob Kuka's book. I think those would be a nice entry point. Unfortunately, most of the things that are recommended as entry points are so dense, and they require so much more that it's very difficult to get into them. But I would say that those two are the things to look at. That I find them very useful. There are lots and lots of internet resources now.
Right.
You just need to Google what is quantum computing, and you get some high quality videos from Microsoft and from Amazon, etc.
Right.
And if you really want, there's a TED talk as well, which I gave. It's a terrible TED talk, but there's about 5 minutes of the 18 that are useful.
Okay. Yeah, I hope the moderators will put a link to it in the chat, so keep an eye out for that. Quick question: does Moore's law apply to quantum computers?
Well, no, for the simple reason that it's I'm not being straightforward. So I think it will. I think there's a measure of quantum volume or quantum effectiveness that will allow us to look at things as they expand. So I think, yes. Okay. What is it? We don't know. So my company has said that we will double quantum volume every year, right? Double every year. So that's faster than Moore's law, right?
Right.
But we're still at the early stages. We're starting at a low base. So in 10 years' time, will it still be doubling every year? I don't know. I reckon it'll probably be faster.
Wow.
Yeah. That's my sense, right? That's my sense. But so I think the answer is yes, there will be, but we don't know what it is.
Some limiting factor we discover along the way.
Yeah. Okay. Yeah. Well, hopefully somebody in India.
I really hope so. I mean, the kind of motivation that you've given to the audience today, and I mean, really, thank you for being here with us at India Science Festival. It was fantastic talking to you. I really hope we can host you again next year as well.
But hopefully in person.
Hopefully in person. Definitely.
Yeah. Thank you, everybody.
Thank you.
Real pleasure. Bye-bye, everyone.
Bye-bye.